Okay, so a while ago we learned how to solve third order differential equations using methods of undetermined coefficients. Okay, in this example we learn how to solve higher order differential equations using variation of parameters. Okay, so we have let's take a look at this example. Okay, so y triple prime minus y prime is equal to 2 over 1 plus e to the x. Okay, so this is a third order differential equation. Okay, so in order to solve this one, let's first find the roots. Okay, we write m cubed minus m just equal to 0. Okay, and m is just equal m squared minus 1 equal to 0. Okay, we just factored it out, and we have m is equal to 0 and m is equal to plus and minus 1. Okay, so these are our roots. Okay, so since we have distinct real roots, so we can write our y particular in this form: a plus b e to the negative x plus c e to the x. Okay, this one has we will write this one as a e to the 0, but since e to the 0 is just equal to 1, so this is just a. Okay, so this is our complementary function. Okay, so next is we need to find yp. Okay, in order to have our general solution, which is equal to yc plus yp. Okay, so we need to find yp. Okay, in order to find yp, we have an equation: u1 y1 plus u2 y2 plus u3 y3. Okay, so we need to find the value of u1, okay, u2 and u3, but our y1, y2 and y3 are already known. Okay, y1, okay, it's just equal to a. y2, it's just equal to e to the negative x, and y3 is just equal to e to the x. Okay, so we need to find u1, u2 and u3. Okay, so we are now solving variation of parameters. Okay, so in order to find u1, we have this formula: u1 is just the integral of w1 over w. u2 is just equal to the integral of w2 over w, and u3, it's just equal to w3 over w. So this is how to find the values for u1, u2 and u3. Okay, so what is this w? So w is just our Wronskian method or Wronskian determinant. Okay, in solving variation of parameters to find the value of u1. Okay, so in this equation, okay, or in this higher order differential equation, okay, we need to find the value of w. Okay, w and w1, the corresponding w's. Okay, so in order to find the different w's, we need to use 3 by 3 determinant. Okay, so to find w, we have here 1, 0 and 0. Okay, 1 is from, so like a. Okay, this is y1. Okay, y1, y2 and y3. We differentiated those y's, okay, to form this 3 by 3, it's like Wronskian determinant. Okay, so we have here -2, so I presume that you already know how to solve using 3 by 3 matrix. Okay, so w is just equal to -2, and this one is the formula on how to solve like w1. Okay, so this one, you just replace the y column by 0, 0 and f of x. Our f of x a while ago was 2 over 1 plus e to the x. So that was our like f of x. So we just substituted that one here. So because the formula is 0, 0, 2 over 1 plus like f of x. So this is our f of x, our y2 and y3. Okay, the answer of that one is just negative 2. Okay, you can just check it out if you're really eager to learn. Okay, so we have here w2. Okay, just replace the second column by 0, 0, f of x and retain the original like values for the first and third column. Okay, so next is the answer is negative 2e to the x over 1 plus e to the x. And lastly, we have w3, which is equal to this determinant. Okay, 1, 0, 0 e to the negative x. Okay, this one, and this is our 0, 0 and f of x. The answer is just negative 2e to the negative x over 1 plus e to the x. Okay, so this is how we find our answer, like the values for w and w1, w2 and w3. Okay, so now we are now ready to solve for u1, u2 and u3. Okay, solving for u1, u2 and u3, we have here this like sheet of paper. Okay, this one u1. Okay, I said a while ago that u1 is just equal to the integral of w1 over w. Okay, our w, okay, let me just check it out. Okay, our w1 was like negative 2. Okay, and our w was negative 2 also, so we get negative 1. Okay, negative 1. No, not negative 1 but positive 1. Okay, integral of 1 is just equal to x. Okay, w2. Okay, our w2 a while ago was this, negative 2 e to the x over 1 plus e to the x over negative 2. Okay, so this is our integrating like function. Okay, so we integrate this function. Okay, I presume that you are really good in like integrating functions, so we must let this like 1 plus e to the x, let this one is it is equal to u. Okay, so solving that one, du is equal to e to the x dx. So therefore we can rewrite our like function like this, 1 over u du, and its integral is just ln of u, which is our u is just equal to 1 plus e to the x. Okay, so this is our u2. Okay, u2. u3. Okay, u3 is just equal to the integral of w3 over w. Okay, again we subtract. Okay, I just simplified this one earlier. Okay, negative 2e to the negative x over negative 2 1 plus e to the x. Okay, so negative 2 will be cancelled out, so we do the integration. Okay, to integrate this one, we multiply e to the negative x over e to the negative x to our function. Since this is just equal to 1, okay, so it's just like we are not multiplying something. Okay, this one will just be cancelled out. Okay, but in order for us to integrate this one, we need to multiply this one. Okay, so e to the negative 2x over e to the negative x plus 1. Okay, distribute this one. Okay, e to the negative x, e to the negative x over e to the x. Okay, is just e to the x over e to the negative x is just equal to 1, so we get this one. Okay, and let us let du u is just equal to e to the negative x plus 1. Okay, e to the negative x plus 1 and du, okay, negative e to the negative x. In order for us to get the equivalent u function of e to the negative x, so like e to the negative 2x, we need to transpose 1 to the left hand side. Okay, u minus 1, and square it. Okay, square it to get e to the negative 2x for us to have a substitution here. Okay, e to the negative 2x, so we have u minus 1 squared, okay, over u. u minus 1 squared is just equal to e to the negative 2x. So this is it. U, okay, it's just equal to 1 plus e over x. This one. Okay, so this function is really the same as this one. So integrating that one, we get u squared over 2 minus 2u plus ln of u. Okay, substitute the values for our u, we get e to the negative x plus 1 squared over 2 minus 2 e to the negative x plus 1 plus ln of e to the negative x plus 1. Okay, so that is how we integrate those functions and how to solve u1, u2, and u3. Okay, so next is we need to arrange now our yp. Okay, I said a while ago that our yp is just equal to this formula or arrangement. Okay, so u1 times y1 plus u2 times y2 plus u3 times y3. Okay, u1, okay, our u1 a while ago was just x. Okay, and a, we presume a while ago that our a was just equal to 1. A is just any constant, so we can let that a be any constant. So to make our calculation simpler, we use 1. Okay, plus e to the negative x. Okay, our y2 a while ago. Okay, this is our y2, e to the negative x. u2 is ln of 1 plus e to the x plus e to the x, which corresponds to our y3, times this very long function value for u3. Okay, we can simplify this one. Okay, we can simplify our yp, okay, to get this form. Okay, maybe you have a lot of ideas how to simplify this one, so you can simplify this one further. Okay, since we don't have enough time here, so okay, I will just let this one simplified by you. Okay, so our yp is this very long yp. So therefore we have our yc and yp. So now we can form our general solution for our third order differential equation. Okay, so our y, okay, our general solution is just equal to a plus b e to the negative x plus c e to the x plus x minus 1 plus e to the negative x ln of 1 plus e to the x plus 1 half minus e to the x times 3 halves minus ln e to the negative x plus 1. Okay, so this is our general solution to our higher order differential equation. So okay, so as of the moment, you already know how to solve methods of undetermined coefficients and variation of parameters. So I hope you apply this one as you learn higher order differential equations. Okay, so see you next time.